So this video is actually a sequel to another one. So recall back to when I did that video, I think it was titled "The Value of C is Left as an Exercise for the Viewer." It was basically just this same general style, but with f of s equals to s to the x. Now, this is a more generalized version, and indeed it does seem more scary. We have the double prime of x times f, and then minus the square of the first derivative over f squared. And then here we basically have the antiderivative. And this one, there might not be an exact value, because that would be kind of overpowered, but we can write it in terms of other functions, for like we did in that video. So first of all, this thing here, this f squared of x is the main thing that should catch someone's attention when you first realize this. Because if you recall to the quotient rule for derivatives, right? The dx of f over g. Here, f and g are shorthand for functions. This is going to be equal to the derivative of f times g minus the derivative of g times f over g squared. You can derive this from the product rule if you set 1 over g is another function, and then so on and so forth. You get this expression. You get this expression, right? So here we have a g squared in the denominator, and here we have an f squared in the denominator as well. So here, this g function, which is going to be these two, is just going to be f. Because what we're saying here is that we want to set this expression to be the derivative of something. Because, well, then we can apply integration by parts, and then we can differentiate this, and that'll get rid of a lot of things. So that's nice. Oh my god. My things keep falling today. Anyway. So the signs they're good. So f prime times g is f double times regular f. But here we already know g is going to be f, so that means f double is the derivative of this. So basically, this f is just, this numerator is just the derivative of our f here. So here we have this integral is equal to the integral from 0 to t of the derivative with respect to x of f prime x over f of x. And then this integral here. Okay, so that was a nice first step. We now have a clear way forward. So if you were to integrate this by parts, the first thing is just to be this times this, and then evaluate it for this, and then subtract this. So, first of all, we have f prime, and then this entire chunk just evaluated at t. And then here, minus this 0 thing. Now, if you look at this integral, if you plug in x is equal to 0 to this thing, it's going to be an integral from 0 to 0. So the bounds are the same, which means there is no integral, which means the value is 0. So we can just ignore this bit. And then we can continue on to the integral part, which is going to be minus the integral from 0 to t. And then the derivative of this is just going to be f of x. And then we have f of x 1 over f of x times f of x. So those will cancel. And we get f prime x. And then derivative, we have a derivative here, and then we have an integral here, so that cancels out, and then we just have to plug in these two values. So, we have a quick answer. Oh, it's rather quick, to be fair. F of t, and then we have an integral from 0 to t. S in this case doesn't matter, so I'll just replace that with x, because I'm used to writing x, and then minus, and then first of all we have f of t, and then minus plus f of 0. Very well. So this is probably a very short derivation. It only took about 4.5 minutes. But the biggest thing, the thing I like most about this sort of style of integrals is it's really easy, and it creates some really intimidating integrals, and that's what I will spend the rest of this video on, just plugging functions and see what they get. Now, once again, the original video, the x to the x thing, that was kind of a special case of this thing. So I'm not gonna write that as an example because, well, you can just watch the other video. What we can do is here we want things to look weird. So we need to find functions whose derivatives are wildly different from themselves. I mean, the sine's derivative is cosine, and the derivative of cosine is just going to be negative sine. So it's sort of the same thing. So we want something new, we want something different. And my first candidate, because there's multiple, the arctan function. And I wrote that 3 lines equal mark because I just thought it looked fancy, but then I realized, well, my job isn't to look fancy, so I just got rid of it. So now with the arctan, the derivative of t is just 1 plus t squared. It's wildly different from anything related to inverse trigonometry. And now if you were to take the second derivative, I'm probably going to have to box this off because this might interfere. Now I have the second derivative, f double prime, is equal to, okay, so derivative of this. Using the chain rule, we have a minus, and then the derivative of this is going to be 2t over, so minus 1 over this thing squared, so 1 plus t squared, and then of course the derivative inside is just over there. And then we have this integral term, the integral from 0 to x f ds. F is once again shorthand for a function. Now, this one is going to be s times, wait, no, the answer is not going to contain s, this is a definite integral. So we have, x arctan x, and then minus, I think it was like 1/2 natural log 1 plus x squared. And then minus this constant 0. I mean, minus this function at 0, but it's going to be 0, so never mind. Is this correct? I think it is, because it was minus the integral of x over 1 plus x squared. You times it by 2, so that one has to be 1/2. And so, yeah, I think that's true. If it's not, then you can always correct it, but never mind. So now, if we just plug this into our expression, we have, and to make it look more pleasing, I'm going to choose t equal to 1. Okay. Now, I think it's best if we look at this expression bit by bit. So, here f and f squared will cancel. I mean, this f will cancel. So, we have f double prime over f, which is going to be this thing. Negative. And then 1 plus t squared on the bottom. Squared, of course. And then the arctan t, and then over 2t, and then minus, and then it's going to be f prime over f, the entire thing squared. So it's going to be, yeah, so going to be 1 plus t squared, arctan of t, this big thing squared. Now once again, okay, so first of all, these two negatives, we can factor that out. So we can just get rid of that very quick. And then we have the integral. So we have this is going to be x arctan x. This integral is actually quite big, actually. Minus 1/2 natural log 1 plus x squared dx. And I'm going to have to clear up this a little bit, because my whiteboard is actually getting kind of dirty. Okay, so we want this expression with t equals to 1. So f prime of 1 is going to be 1/2. Yeah, 1/2. And then over f of t, arctan of 1 is going to be pi over 4. If you were to take the reciprocal, we have 4 over pi. Over, no, times. If you plug 1 to here, this is going to be pi over 4. And then minus 1/2 natural log, this is going to be 2. And I'm running out of room. And then minus our tin one, we know that's going to be pi over 4. And then plus f of 0 is going to be 0. So I'm going to slightly clean this up a bit. So 1/2, that's going to be 2 over pi. Okay, so first of all, for this first thing, these two will cancel. We have 1/2, so we have a 1/2 up front. I'm just temporarily writing it here. This is not multiplication, by the way. And then we have 2 over pi, and then minus 1/2 natural log 2. So 2 and 1/2 cancel. There's going to be a minus, and it's going to be 1 over pi times natural log of 2. So minus, let's see, what was it? 1 over pi natural log of 2. And then finally minus pi over 4. And then I'll erase that. Okay. Righty. Now once again, we can change these two signs, because it's a common factor. We can change it, and then we can put the negative over here. So basically what we're going to do is we're going to replace these two terms. And then change this to a plus. So we have pi over 4. And then minus 1/2 here. And this is the integral expression you get. Now, I found a pattern, which is when pi shows up in the denominator, the integrals get complicated. So apparently, from my standard, this is a complicated integral. But if you were to look at it like this, it's actually really easy. I did it in like 4 steps. So this is basically a intimidating integral generator, pretty much. And this was for the octet function. I mean, you can do a whole variety of different functions. Maybe one exception would be exponentials, because, well, their derivatives and antiderivatives are equal to themselves. So from that standard, this would be a constant. So this entire thing would be 0. But, ignoring all this for a second, f of 0, the exponential of 0 is going to be 1. So there's going to be some difficulties over there. But for most functions, this gives you a very complicated function. Perhaps I'll end it to that. You can just try and play it around, or just show it to some random guy on the street. They're probably not gonna do much, because, well, they're a random guy on the street, but it's pretty intimidating, I'll say. So that's it for this week's video. Once again, I can't make promises on the next, but I'll try my best. See you in the next one.